let's go ahead and demonstrate how the Morse circle is useful in the calculation of principal stresses and eventually directions, the angles associated with the rotation. So I'm going to start off with two examples that are fundamental, and those examples we've also considered before. The first one is a rod under uniaxial tension of 100 MPa. So here we're really looking at a point where the state of stress is represented geometrically as tension. All the units are MPa, so I'm not going to write it explicitly again. Goes without saying, on the opposing faces there are similar stresses. So the coordinate system here is x and y. That's the original picture that we are dealing with. So the second fundamental example that we looked at was the case of not pure tension but pure shear. So directly writing the state of stress, geometrically representing it with respect to an original system x, y. The value of the shear stress was in this case 10 MPa. Okay, good. So I'd like to go ahead and solve the principal values again. So here I know that this is already a principal normal direction, this is already a principal shear direction. I'd like to calculate the other ones through the concept of the Morse circle. So these are two simple cases, and therefore it will help me quickly construct the Morse circle. And so the first step is always to go ahead and draw my map, the axes all associated with the Morse circle. So here, both of them sigma tau plane, okay? And the subsequent important step is the correct identification of the 2 points. So I will have 2 points. The first point, the x point, remember, is the point sigma x minus the value of tau xy. So presently that point is equal to 0, 0, because that's what I have here. And the y point is the point that's associated with sigma y plus tau xy. I'm not going to write plus from now on, so that's equal to 100, 0. So the first point that I'm going to put on the map, it is the x point, which is located over here. And the second point I'm going to put on the map, so that's the x point, 0, 0. And the second point is the y point, which is associated with the 100, 0 point. So that's going to be over here. That's the y point. So when I say the y point, I mean the plane with the normal y. So that is 100, 0. Now, once I have that, I can do immediately two things. So first, of course, I can draw the Morse circle. It's clear that it's going to be like this. And I can immediately identify its center, which is a equals sum divided by 2, so 100 plus 0 over 2, 50. And the radius is obviously, in this case, trivially equal to also 50. And therefore, this is already a principal direction. If I rotate on the Morse circle through an angle of 2 theta s equals 90 degrees, in other words, theta s equals 45 degrees, which I immediately conclude from this, so I don't need any equations, I will reach a plane where the shear stress is an extremum, plus or a minus is sufficient to indicate 1, and that value is at a r, or the other one is a minus r. Therefore, the value of the principal shear stress, which therefore is going to come from that point, we indicate that with tau 3, which is equal to simply radius, which is 50 MPa, as my analysis indicated earlier. In fact, here we already know that these are the principal directions. If I indicate this as sigma 1, it's already equal to 0. And sigma 2, if I interpret that to be the principal associated with y, so 2 for y, 1 for x, that is already 100. So that's easy. Okay, so the second example. The second example, again, I start with the original picture, and I want to draw the Morse circle. The first, I identify the points carefully. The first point is sigma x minus tau xy. In this case, again, x is 0, but minus tau xy tau xy here, notice that here I had this equals sigma y, here I have this equals tau xy. Okay, if it were in the other direction 10 MPa, it would have been tau xy equals minus 10 MPa, but here it's plus. But here I have to write minus, so it's 0 minus 10, and the y point is, the convention is sigma y plus tau xy, so it is 0 plus 10. So now I can go ahead again, put those 2 points on my map. The x point goes over here. Minus 10. And the y point goes up there. Okay. So now that I have those 2 points, I can easily draw the Mohr circle and conclude the values of the principal stresses. So first of all, the Mohr circle, I can easily draw it to be that, right? And the center obviously is at a equals 0. And the radius of the Mohr circle clearly is equal to, again, in this case 10. Just like here, it was easy to identify. Therefore, I can easily calculate that when I rotate in the counterclockwise direction, this point is going to go, after a rotation of value equal to 2 theta n equals 90 degrees, so 45 on the physical picture, 90 on the Mohr circle, but in any case, in the same direction, counterclockwise direction, I will get sigma x going to sigma x prime to eventually sigma 1, which is a value of plus 10, and the value of sigma 2 will be minus 10 MPa, which is consistent, all of which is consistent with what I found out earlier by making use of the equations explicitly. So we can go ahead and now solve a slightly more complicated example. Now that slightly more complicated example is based on a given state of stress. So now that state of stress can be given to you explicitly or geometrically. So in this case, let us provide it explicitly. So sigma x is equal to 80, sigma y is equal to 40, tau xy is equal to 30. Goes without saying, here in my examples, everything is in MPa. So the corresponding picture would be that picture. So that's x, y, this is 80, this is 40, and that is 30. And I would like to calculate the principal stresses and the directions. So I'm going to go ahead and draw the Mohr circle once again. So that's sigma, that's the tau axis, so that's where I put everything on the map. And first I go ahead and identify the points correctly. First I go for the x point. So the x point is, again, here I'm writing, reminding you again and again how to pick those points. So it's sigma x minus tau xy minus 30. The y point is going to be sigma y plus tau xy, which is equal to 40 plus 30. And the Mohr circle is so critical to many of the things that we're doing. We should get a good grasp of it. So now once we have those values, then I can go ahead and put them on this picture over here. Now it's a little bit more tricky because it will have two values along two axes, both of the points. So now the first one is going to be at 80 minus 30. So let's say it's a point probably, let's say over there. And the second one is 40 plus 30. So if that's 80 and say this is 40 over here. So plus 30. So that's the x point. 80 minus 30, and that's the y point, which is 40 plus 30. So once I have that, I can now go and first draw the dial. That's going to help me draw the circle. So that's my dial that I will turn depending on the rotation that I want to impose. And the center of the dial is at 40 plus 80 divided by 2, so that's 60. And the circle is going to look like this. Okay. Now, the radius of the circle, if I want to calculate that, right? So this point is 80. So we can go ahead and do that together, which is rather simple, right? So it is 80 minus that, so it is 20 squared plus that distance, which is 30 squared. Sorry, I repeat that. So 80 minus 60, 20 squared plus 30 squared, square root. So it's going to be, let's say, 36.05. So that's going to be the radius. Now, if that is the radius, I know that these points are associated with shear stress, so remember, these are the principal values. That's the maximum normal stress I can calculate for any possible rotation, and the maximum values I encounter are here, sigma 1, which is the center A plus R, so in other words, it's going to be 96.05, or it's going to be sigma 2, which is 60 minus that value, so in other words, 23.95. Okay, that's easy. And this angle is equal to twice theta n. Okay, and twice theta n satisfies that distance, which is 30, over that distance, which is 20, and you can easily calculate and solve and obtain exactly the same value that we eventually obtained before, which is 28.15 degrees. Good. So let's put that on the side. Now, additionally, what we can concern ourselves with is the maximum, the principal shear stress, which is going to occur on a plane that's rotated like this. So this would be 2 theta s. Always you see that this rotation differs from that rotation by 90 degrees on the Mohr circle, or 45 on the original one on the physical picture. So theta s is theta n, let's say, plus 45 degrees, which is the same answer, 73.15, that we got earlier. And the what we call tau 3, the principal shear stress associated with these rotations, it's equal to simply the radius, which is 36.05. And so we obtain exactly the same things, right, without making use of any equations that need to be memorized, right? We only need to understand how to put things on the map and then interpret the results accordingly. So we can quickly solve for yet another example. Now that example we have not solved before, so let's quickly do that as yet another example. So that example is as follows, and here my goal is to get you to think about also the picture that we are providing. So this is the state of stress at a point, it's geometric depiction. So we have the stresses depicted like this, so everything is in terms of MPa. I'm not going to write the others. The shear stress is in that direction and that direction of value 40, and there is a normal stress here as well, which is 40. And I like to draw the Mohr circle. Now before you do that, right, always remember that we have to identify the components of the stress accordingly. So sigma x is 20, but it's compressive, so I have to attach a minus sign. It's minus 20. It doesn't matter whether it's positive or negative. Sigma y is already tensile, so it is plus 40. Tau xy, the default direction on the plane with normal x in the direction y, the direction is reversed, so it is minus 40. So those are the stress components that are associated with this picture. If we identify them incorrectly, everything else obviously is going to be incorrect as well. So then now we want to go ahead and draw the Morse circle. And now as we do that, the first step, as usual, is to identify the points correctly. So we're going to have an x point, which is sigma x minus tau xy, which is going to be minus 20, minus minus, it's now going to make 40, right? Minus the shear stress is plus 40 now. And the y point is sigma y plus tau xy, which is now 40, and then plus tau xy, which is minus 40. Okay, good. So now we go ahead and put those on our our map. And the first point is the x point, so it's minus 20, 40. Let's put that point over here. And the second point is plus 40, minus 40. So maybe over here. Okay. And so that's the x point. And that's the y point. And now we can go ahead and connect these two. That's our dial, that's the diameter of the circle, that's the center A, which is in the middle, so it's minus 20 plus 40, 20 divided by 2, so that's lying at a value of 10. And I can calculate the radius, but before that, let me draw the Morse circle. So that's the circle, and the radius is going to be here. So the radius is equal to, so now again we can calculate it together. So it is, let's say if we look at this picture, 40 minus 10, it's 30. It's 30 squared plus this distance is 40, 40 squared, so 3, 4, 5 triangles. So the radius is nicely 50. So you see you don't have to really memorize anything, just follows nicely. And then if that is the radius, then I know that this here is sigma 1, which, well, let's call it sigma 2 because it has to do with the rotation of y. That's the way I'm going to interpret it. So it is 10 plus that, it is 60, and this one is 10 minus that value, which is minus 40 MPa. So that is, with my notation, sigma 1. And the principal shear stress occurs over there, that's tau 3, and that's going to be equal to the radius, which is 50. And so this angle over here, it is twice theta n, and so you can calculate that twice theta n to be 53.13 degrees. So theta n is half that value. Okay. So what we've obtained is the Morse circle from which we can easily calculate the normal stresses and the shear stresses. Now, among all of these examples, and eventually when we make use of the Morse circle towards failure, that's how I motivated everything. Among all of these, the one picture that's very important is always the principal picture, what I will refer to as the principal picture. And without stating it explicitly, I'm going to always mean by that the normal directions, okay? Principal normal directions. So in other words, this picture will be indicated alternatively. The state of stress will be indicated with respect to the principal normal direction. So in other words, that angle is theta n, not theta s. And that picture corresponds to a state of stress represented geometrically at the same point, but with respect to a rotated picture, and that picture has a sigma 1, which is compressive and minus 40, so it's in the other direction, and a sigma 2, which is 60 MPa, it's tensile, and there are the other ones as well. But there is no shear stress because this is a principal direction. This point is 60, 0, this point is minus 40, 0. The shear stress is 0 as it should be on the principal direction. So This is the always what I will refer to as the original physical picture, and this is the principal picture. Okay, so because it is such an important picture in our minds. Now, so therefore, when we talk about rotations, I'm representing the state of stress either with respect to, well, that's the original representation of the state of stress, but really this is an equivalent, but just a different picture of the same state of stress. So when I talk about rotations with respect to towards arbitrary planes, okay, so I can start from a rotation with respect to the original picture and go to another picture. In particular, I can go here, or I can start from that picture and go to another picture, in particular to over there. It's all the same state of stress. I can also go to somewhere in between, either starting from here or there. So my reference axis could be xy or it could be 1, 2. Doesn't matter. That's why we call this tau 3 in some sense, because I have originally 1 and 2, and then I rotate in that plane. And when I rotate, I can hit that plane or some other plane, right? I start here, and if I rotate minus half of that, I would go to this picture, or if I can go to the principal shear direction, right? And the rotation, therefore, can be described with respect to the principal picture, just as well as we can do so with respect to the original picture. And so it's 1, 2, I pick the third one to be 3, tau 3 in this case. Sometimes people call this tau 1, 2, meaning that this is the principal stress associated with rotations in the 1, 2 plane. But this is just as well a notation as the other one. Okay, so this picture holds a place that's going to be very important for us, and so I wanted to highlight it at this point. Again, it is just the principal picture representation of the state of stress at a point. It's the same state of stress, it's just another way to depict it, which we determine through the Mohr circle.